I'm coming completely left of field. You'll see that my background really is renal, kidney transplant, and paediatric surgery, and research basically. And I was minding my own business back in 2008, doing ECMO work, comparing that with cold perfusion of pigs to see which was the best. And I was reanimating these kidneys through an ex-vivo system that we just created, which basically was a bowl, a pump, and an oxygenator, just to show that ECMO was actually slightly better. This is an example. This is podocytes from the glomerulus, and you can actually measure the distance, the thickness of the podocyte between the tubule and the vessel. And that's an example of cold, and that's an example of ECMO, and they look pretty similar, but you can actually compare the distance, the width. So the left-hand side is this one's the cold, and this one's the warm. And if you cock it up, it's if you cock it up, it's actually for ECMO it's far worse. So we found that ECMO is good provided you do it properly. And whilst we were doing this, we came across a chap called Rees, who developed a solution whilst he was lecturing in biochemistry in New Zealand. And it was used really as an illustration for students, for hearts working, and the hearts they used were rat hearts. And he claimed that the company claimed that RSI was brilliant for everything, and we didn't quite believe in for storage and for warm reanimation and so forth. And basically it's just salty water with a fair bit of salt and potassium in it, and this is the contents. And the osmolality is actually quite low at 286. And if you compare that to the other solutions around, you see the osmolalities in storage solutions is generally quite high. And Krebs Henselate and RSI, which is a reanimation solution, is isotonic, and therefore you expect things to work with it. Now the other chap we came across is a chap called John Brazil, who developed a company called Functional Circulation that manufactured this Model 30, and it's really designed for warm reanimation of organs. And we purchase it for using with kidneys. And basically it's a heater, a mixer, and a pump. And it also has an oxygenator in it, but that wasn't so good. So we augmented that. And we found if you used RSI as a storage agent for the podocyte width, it wasn't very good. UW was better. And if you use RSI as a flush, it was somewhere in the middle. So we were trying along with our hearts, with our pigs for kidneys. And so for one kidney would be treated with normal storage and the other one with an oxygen flush. And in this series of 3 pigs, we obviously had 3 hearts. So we started working with hearts. So the donors were all DCD donors. They had a general anaesthetic. Death was usually by overdose of anaesthetic, but sometimes it was exsanguination. Sternotomy, and the heart was removed, and the warm ischemic time varied between 12 and 30 minutes. And then we perfused the heart with oxygenated RSI at room temperature, and they had 2 hours of cold storage and then reanimation on a rig. That was the rig we used. It was developed from the Model 30, so it had a ventricular or an aortic sort of pressure inflow as well as an atrial inflow. Now, when you actually have death with a DCD situation, if you look at the lactate level, it rises from the point of death, which isn't surprising. If you have ECMO, it actually continues to rise, but what you're not seeing here is the escalation of pyruvate. So the lactate pyruvate ratio actually gets better. If you cold perfuse, you actually wash the lactate out. So what we decided to do was to try and reoxygenate the hearts in the cold phase after we take it out. So we use machine perfusion. Now this is a cold machine perfusion from a kidney. So we actually just put the heart in it. We used UW, and we actually bubbled oxygen through the solution, and it was very effective. It actually reoxygenated this fluid. And then we rewarmed the heart with RSI and donor blood in our system. Now, by doing that with the DCD, we only found one of the hearts actually we managed to reanimate, so it wasn't very good. In retrospect, the machine perfusion we used wasn't good enough because the pump flow wasn't fast enough, because it has to be quite high to actually close the aortic valve, and this one wasn't. The other thing we noticed was that the lactate was very high, potassium was very high, and therefore we felt that we had to dialyze the hearts. So in the warm phase for the next 6 hearts, we actually put a dialysis filter into the system, and that was very effective at bringing the potassium down, bringing the lactate down, improving the situation, but we only managed to get 2 out of 6 hearts to be successfully reanimated. So another work that we've done was on venous persufflation. Now, this work has been pioneered by the Bond group, where you actually connect your organ straight to gas, straight to oxygen. This is a pancreas that we did because we were interested in doing this for actually getting islets out. So you connect the oxygen up and you pump oxygen through it at 10 to 15 millimeters mercury pressure, and you put some holes in the spleen in this case, and forcibly push the oxygen back through the pancreas. Now, this is islets from a pancreas with minimal ischemia, so what we have is pale blue and dark blue. The pale blue is the absolute number, and dark blue illustrates the islet equivalent, so it takes the size of the islets into account too. If you go cold, if you have minimal ischemia, you have about 400 islets from a rat, and if you have warm ischemia and then cold static storage, you sort of knock that down to about 150, and you can actually improve it slightly with machine perfusion, but venous oxygen actually brings it back up to the minimal ischemia, so it's quite effective. So we thought we'd try this with the hearts. So the heart was connected to an oxygen supply to the right atrium. Oxygen was forced back through the ventricles. We made about 16 holes in the muscle with a needle. This always horrifies cardiac surgeons. And by doing that in the cold phase, we actually managed to reoxygenate the organ such that all of them worked afterwards. This is a heart that had 29 minutes of warm ischemia, and that was, I know, looking at some of these things, I wouldn't fancy myself. I don't think they work brilliantly, but they're not too bad considering. Now our circuits actually got a bit better, so that we've put in a paediatric dialysis filter, which is maybe slightly better than the adult dialysis filter that we had in there, and you can reasonably well control the dialysis of the circuit, and you combine that with an oxygenator, but otherwise the system is as it was, and that's what the whole thing looks like. So we know that you can get hearts out of non-heart beating donors or DCDs, and the Cambridge group have done this, and so have the American groups over in Denver. So in summary of this part of the talk, cardiac reanimation is possible after death. Cardiac death imposes an ischemic death on all organs, and basically with organs, this debt produces either primary non-function if the debt is big enough, or delayed graft function, and obviously that's a big problem for a heart. Why should it be different? Why should the heart be different? Probably the high energy requirements of the heart makes the issue more of a problem, but otherwise it should be the same. So normothermic isotonic solutions can be used for an oxygen flush or as a neutral environment for reanimation. Oxygen debt can be corrected in the cold or in the warm phase. Machine perfusion or persufflation can be used for this, and then you can actually reanimate the organ on a rig. So these are some of the people who have been involved. Now, parallel developments, I have to quickly go through this. So the Transmedics people, who I know you all know about, come from Massachusetts, and they've got a dynamic system. So there the oxygen is pumped through the oxygenator and into the aorta, through the coronaries to the right atrium in the unloaded situation. And when the heart is working, they actually let the circuit go quite right round the heart. So what have they been up to? Well, we've got the PROTECT trial, which is basically the European safety and performance of organ care systems, where they actually put 20 patients into the system. And they had a mean pump time of 3.7 hours with all of the hearts working. From that, we went to the PROCEED-2 trial, which is designed for 128 patients, 64 standard versus 64 on the Transmedic system, and looking at patient survival and cardiac serious adverse events. Now, that trial hasn't actually finished. According to the Transmedic's website, they've done 125 cardiac transplants, either in the trial or non-trial, by October 2011. Why hasn't it finished? Well, obviously, cost must be an issue. I don't fully know about this, but there was a publication by Paddock reckoning the difference was between $100 and $200,000. I think that probably is a bit of an exaggeration, but it probably takes in the developmental costs. The Cambridge group, using the DCD donor hearts, are aiming to use the Transmedics for their hearts. Now, this is Stig, who looks a bit like a character out of a Scandinavian noir crime film. And on his website, he's obviously developed his own system, and the website claims that they've done 70 orthotopic porcine heart transplants with up to 24 hours of warm ischemia, with short recovery periods after, and their aim is to go for a longer term recovery before actually using it on humans. The OrganOx people, this is based in Oxford, have developed a system which is really designed for the livers, but in the background they're thinking hearts too. But at the minute their system wouldn't actually take hearts, and that liver trial with humans has actually started now. So what's the future? Marginal brain dead donors, there'll be more of them, as you all know. There are going to be more donors after circulatory death. So hearts of such donors will need either oxygen resuscitation in the cold, and then you will need some form of assessment. So you can do that in the cold, or you can do it in the warm, or both. So ex-vivo perfusion, the cold obviously is the cheapest, the warm is expensive, and if it's mobile it's even more expensive. The cost is reduced if the ventricles are adynamic, and if the ventricles function is assessed by a balloon catheter, and that's